Okay, good morning everyone. So last week we have already discussed some equation and some basic characteristics for three different distributions. One is a normal distribution, exponential distribution, normal distribution, and also we talk about the exponential distribution and also the log normal distribution, and the last one, which is Weibull distribution. So today we will move on to discuss more about this distribution and how, in the future, how do we apply this analysis. So first of all, this is one of the example that we try to build up. This is what we generally call as a Weibull plot. So this is a Weibull plot with considering the bonding path cohesion. So this is the case whether we start to see our bonding path has certain degradation, and the degradation here is correlated with cohesion. And as we already know, the Weibull distribution has two important parameters, where is beta and alpha, as shown here. So this is a general, like the plot, whether in the future we have to build up the similar Weibull plot that can help us to analyze our value data. And here's some more information related to last week we have been discussed. So first one, last week we have also talked about this specific case, what we call the Rayleigh distribution, where the beta is equal to 2. So the beta is equal to 2 that means here. So this means our failure rate, our hazard rates increase linear with respect to time. So therefore, the Rayleigh distribution are not normally used to describe reliability of an electronic product. However, this distribution appears in the application of the cohesion values. So that's a certain degradation related to the cohesion values, and we can use the Rayleigh distribution. And one of the important characteristics for this distribution is with a case of a beta equal to 2 as shown here. So we can have linear increase of a failure rate. So this is the mention here, the hazard rate increase linear with time. So that's the most important feature with considering this Rayleigh distribution. That's a special case of the Weibull distribution. Okay, so then the question come to us is that how do we differentiate the log normal and the Weibull distribution? How do we know when we can use the log normal and when we can use the Weibull distribution? Basically, this is the question still kind of like the debate, even at the right moment. If you start to look at some reliability statistic, related statistic data, some people propose using the Weibull distribution, some people propose log normal. But basically, they have some mechanism behind that can give us a guidance that which distribution can be better for our data. So if you look at this, this is one of the examples. So this dot is a raw data. This is dot is a raw data here, and this is raw data. But basically, if we try to fit with the log normal and Weibull distribution, so the left-hand side is the log normal distribution, and the right-hand side is a Weibull distribution. So you can find out that the Bose distribution appears to fit the most of the data set very well. For example, you can see that in the case of log normal, we can fit this data set very well, although there's some inconsistency here. But in the case of a Weibull distribution, we can fit this very well, and there are some inconsistency in this range. So based on this observation, so we can figure out that in the case of a Weibull distribution, we can fit the short times better for fitting with a time relatively short. So as shown in the data set here, basically we can fit this data set very well. And on the other hand, in the case of log normal, clearly it's better fit for the longer lifetime. So that's the main difference currently if we're considering the experimental data. This is experimental data with the bulb values. So this is our live bulb value times in terms of plotting in the log normal or in the Weibull distribution. So we can see both distribution can fit the most of the data set, but the main difference is that the Weibull can give us a better fitting with a shorter time, and log normal can have the better fitting with a longer time. So if we consider in the case of a long-term prediction, so then that would be in the end first how we decide which distribution can be used. It will be highly determined by your goals. So if our goal is for long-term prediction, so that for sure in this case, the long-term prediction, that means we want to predict the result. This is experimental data set, so we have the fitting. But if we want to do the long-term extrapolation at this point, then for sure the log normal characterization is preferred. So basically, with all kinds of distribution function, there's no perfect distribution function can be fit very well in all of the region in the data set. There's always a certain inconsistency, and then we have to figure out what will be the goal that we want to use for this distribution. So in this case, if we want to predict the long-term projection, so then for sure, in this case, this is better, because in the case of a long-term here, we can have the better fitting compared to the Weibull distribution. So that is one of the consideration. And in addition to this consideration, we also have some mechanism related consideration between the log normal and then the Weibull distribution. So basically, log normal distribution tend to apply in the case when gradual degradation occurs over time. So that's the case where we can apply the log normal distribution. For example, this is a degradation over time, which is probably due to the, for example, diffusion effects. or the corrosion process. Or the chemical reaction. So, for example, there are some of the previous study in the early time have been shown that a certain degradation might be fitted for the log normal distribution. But this is coming from the early literature. So in the early literature, already point out, for example, these are the example that of device whose value have been modeled by log normal statistic. But you have to be aware of that this is based on very old literature. To be honest, if you look at the recent literature, I would say sometimes this is not true because our technology is being evolved over time to time, and then of course our degradation will also, the mechanism for the degradation will be changed from time to time. So that also means that with any advanced technology, we have to evaluate again for reliability. We have to understand on the reliability. So based on my experience, I'm not sure that the log normal still true for all these degradation happen in the, for example, the early PNP MESA transistor, bipolar or MOSFET or light emitting diode or laser. Then this still need to be cautious that whether we can use a log normal or not. But on the other hand, there's one topic for sure we need to use the log normal, and that's also the topic where we will talk about in these courses. So as I already mentioned in the introduction, there's one specific topic called the mass transport induced value. So in the case of a mass transport induced value, what we are looking at is interconnect reliability. And in the case of interconnect, we consider you have the piece of the interconnection line connected in this way. So we have the interconnection line here, and then we will apply the voltage, and therefore you have the high current will start to go through inside this interconnection line. So therefore we have the huge amount of electrons will be flowing. We have a huge amount of electron will be flowing inside this interconnection line. And we already mentioned in the previous introduction, the main concern for the interconnection line under the high current operation, which is actually this electron will provide a huge momentum to the atom inside this interconnection line. And if we consider this interconnection line is made by the copper, so we have a lot of the copper atom, and the electron flow in this way will start to transfer the momentum to the copper. So the electron will try to push the copper to move as well. So as being certain time, you will start to see we have the copper will movement inside this interconnection line. But the problem is that the copper will accumulate at some region. For example, once the copper moves to this region, the copper will start to accumulate at this corner. And this becomes the issue where we generally call as a here log. So in this region, the copper can lead to the formation of the here log. And because of the total amount of copper atoms inside this interconnection line are the same. So if you have the certain copper movement to here, that means the copper in this region will decrease. The amount of copper in this region will decrease. And therefore, we can start to see this interconnection line become thinner and thinner. In the end, this can lead to the problem that we call as a void here. So this mass transport induced failure, you can, although we haven't talked this mechanism in detail, but you can probably have a good guess that this value is mainly related to the atom diffusion. So now there's a diffusion inside that drives for this degradation. So that means this is a gradual degradation over the time because of the diffusion effects here. So therefore, we actually will prefer to apply the log normal distribution to analyze in the case of the mass transport induced failure. Sometimes we also call this as an electron migration. So this is the most well-known case that we can apply for the log normal distribution, because inside this mass transport induced value, the main driving force leading to this mechanism is related to the diffusion effects here. So this is something that we will also talk more later on when we discuss the mass transport induced values. And on the other hand, the Weibull distribution appears to be applied in the case where we generally call a concept as a weak link. Weak link of the first of many flaws here. So now we have to explain what does mean the weak link. So the idea of a weak link can be easily understood if we consider a series of the chain. So a series of a chain. So what is a series of chain? A series of chain, just an example, we have the bunch of the circle that being connected with each other. That's what we call the chain, 链子, right? So the weak link concept, this kind of concept can be understood using the series of the chain. And why this called a weak link? Because if one of the connection is broken, the chain is broken. So therefore, if suddenly we have this broken, if we look at the sentence here, that's equal to the first of many flows. So that means if inside a chain, if any of the connection is broken, if any connection becomes the first broken, and then the chain is completely broken as well. So that's why we call this concept as a weak link. So why do we call link? Link, it means because all these events are linked to each other. All these small individual events are all linked to each other. And as long as there's a weakest part happen, all of the total event will have the value as well. So that's why we call it weak link. If this is a weak place and this is the first place that can have the value, and once it happens, this whole chain will have value immediately after the first of the flows. So that's why when we explain this is a Weibull distribution can be applied in the case where the weak link, and what is weak link is a first of many flows here. So in the case of the Weibull distribution, the most well-known reliability case we can use the Weibull distribution is a dielectric breakdown here. This is because when we consider dielectric breakdown, we can also consider that is a case of a weak link. So how do we use this concept to understand the semiconductor reliability, especially in the case of the dielectric breakdown? So now, again, we have the MOSFET here. So this is our gate dielectric here. Now we can try to divide this gate dielectric as a small piece from left to the right. So we can make this dielectric as a smaller one as possible we can. So now this is the dielectric can be considered as a series of the small dielectric. So the whole dielectric here can be considered as a case of the series chain as well, because if we divide by small dielectric, and then the total dielectrics become the connection of all these small dielectric here, right? So now we figure out that we can also apply the concept of the chain here. And of course, once we apply the gate voltage, we plot the gate voltage here. And as you know, we have once we apply gate voltage, we for sure have the electron will be formed inside the channel. But however, if one of these small dielectric is broken, for example, here, then actually all of the current, all of the electron will immediately flow through this small broken dielectric region and become the leakage current. Because if you have already learned the basic electronics, so we all know the current will prefer to flow in the region where has a low resistance. So as long as this region is broken, or as long as this region has, once it broken, it becomes leaky. So that means it has a very, very low resistance. And therefore, all the electrons now will prefer to flow this region. And in the end, induce a huge leakage current. So now you can see this is exactly to fit the concept of the first of the many flows. So that's why, because it fits with the first and many flows, that means also this is a case of the weak link. Right? Because now we transform our gate dielectric as a small part where each connected as a link. And once there's a small region is broken, and that will immediately to make the whole dielectric broken as well, because now the electron will only flow to this region and become a high leakage current. So this concept is exactly similar to our concept of this weak link, or the first of many flows. So that's why if you look at for the dielectric breakdown, more than 99% people are using the Weibull distribution. And there's some exceptional because of the sometimes your dielectric is not just a pure single layer. You have a certain like a bilayer, and then there's some additional consideration. So people will revise a little bit about distribution, but basically the concept is following using the Weibull distribution. So that's a theme here. Many of the engineer, when they try to analyze the dielectric breakdown or dielectric reliability, for sure they know they have to use the Weibull distribution, but most of them, they don't know the reason behind, because the Weibull distribution is not that very complicated mathematically, because once you know how to use, you know how to use for your whole life. But or you look at for the literature, you found that lots of people has been used, so you just follow that. But it's really limited people that can understand why we can use this Weibull distribution. But the good thing is that if we understand, we can make sure that our analysis is right in the case where the mechanism exactly have this case. Because sometimes under the certain consideration, probably we might misuse the Weibull distribution in the case that doesn't have the weak link process, and that will cause the huge issue related to the lifetime extrapolation or the value analysis. So when we talk about TDDB, we will also talk about again why we can use this Weibull distribution, and then in that part you will start to see many of the examples that people prefer to use the Weibull to understand the TDDB case. Okay, so now we have to know how to do the calculation. Of course, in the previous lecture, we have already explained to show you the general form, no matter for the normal distribution or Weibull distribution, and you can see those functions not that straightforward. You can easily use, but it's good for being the engineer. We always try to find a way that can allow us easily use this distribution. So our goal is we need to plot the probability function as a straight line. So a good linear fit of value time and data is required. So then the question arises, how to make nonlinear reliability function plot as a straight. So that's become our question. But the concept here is very simple. So first of all, we have the basic Weibull distribution as shown here, 1 minus exponential minus t over alpha beta. That's our basic equation for the Weibull distribution. Now we just put the natural log in the both sides. So once we put the natural log here, this equation becomes like here. Since we put a natural log here, so then we put a, first we can remove this to here and put a natural log and put natural log. So natural log will cancel this exponential. So then this equation will become like this one. And also one more thing is we apply the natural log again. So then this equation will become, we move the minus to here, and then we have a natural log t over alpha with beta here, and that will become beta natural log t minus beta natural log alpha. So now if we consider the left hand side as a y and the right hand side as a mx plus b, so that means if we consider x is equal to natural log t and n is beta and b is equal to here. So with this, y is equal to nx plus b. So we can plot the equation as shown here, where our x-axis is a natural log, and then the y-axis is a natural log minus natural log 1 minus ft. So with this consideration, we can make the plot as a straight, where as a straight here, where the slope is beta and the intercept is minus beta natural log alpha here. So now with this plot, we can basically extrapolate the necessary parameter inside the Weibull distribution, which is beta and alpha here. So now this simple equation as a straight line is a y equal to nx plus b, where y is equal to this and x and so on are all equal to this as well. Those, the Weibull paper is generated by plotting. So as long as we plot this versus, or we plot a natural log, or we plot log versus a natural log t or log t, so we can have the straight line that allows us to extrapolate the beta and alpha here. So sometimes, because this term is difficult to name because it's a long mathematical term where we call the natural log minus natural log 1 minus ft. So sometimes people just give this term as a name. That's we call the rabbit. Okay, for sure, we can also use the same tricks to plot the log normal distribution as a straight line. But in here, we won't talk in the detail. So we just show the result where the straight line can be plotted in this way, and then the sigma is shown in the following. So another thing we need to consider is when we have a lot of value data. So we have to plot, there are many capital F values to plot. So these will have very difficulty in general generating straight line. That's based on the experience. So we have if our value data, we have a huge data set of our value data, and then we have to plot lots of the capital F plot. That's the cumulative distribution, the value rate here. So that would be very difficult to generate the straight line. So therefore, we have come up with a good estimation. If there are few values, so we can obtain a good estimate for these statistical parameters. So under this consideration, the capital F can be obtained by ranking the exactly value times here. This is a recommended way to estimate a statistical more accurate for this CDF or the capital F population, and this is what we call as a Bernard approximation. So the Bernard approximation is typically used to simplify the calculation of the median ranking, and where our equation is simply shown in here. We have the capital F TI is equal to, we have the I minus 0.3 and N plus 0.4. So the I is the order, and N is a total testing number. And the FTI here is exactly the one we would like to use in the Weibull plot, which is natural log minus natural log 1 minus FT. So this capital F is the one referred to here. This one. In the later, we will come up with an example that how do we will guide you how do you make the Weibull plot using the equation here. For sure, right now with using this equation, probably sometimes a little bit confused, but with a more practical example, you will know how to use that. So we will talk about this in the later. So here is an example for the practical example. In the end, if we plot as a Weibull, that's the left hand side. And in the right hand side, that's a log normal. If we try to plot the either for log normal or Weibull, we plot this cumulative percentage value. So this is x-axis as a cumulative percentage value, and also the y-axis is a time. So ideally, we expect with only these one single straight line can fit our experimental data. But in reality, sometimes we found out that this is our experimental data, but we need to fit this and this with a different fitting parameter. So if you look at this data set, we can really fit this one with a one distribution. We can also fit this one as a second distribution. And this is in the first distribution, is a case of our value below probably less than 5 hours. And in the second distribution is the value between the 10 to 100 hours. So again, of course, for you, if the first time for you to try to fully understand this statistics analysis, sometimes it's a challenge, and then you will get confused how this in the end correlate with our reliability, physics and mechanism. But this is one example how this statistic fitting can help us, because ideally we should have a one distribution data set. Distribution function can fit all the data set. But in reality, we can have the case that we have the bunch of the experimental data, but we need to use the two distribution that can fit. And one distribution is fit with a short term, and another distribution is fit with a long term. But this is actually give us understanding that because they are the two different mechanisms in the short term and long term, that's why we need to apply the two different distribution functions. So the basic information we can have is if we come out with one distribution can fit one certain data set. That's always indicate that we have the first mechanism here. So the first mechanism will lead to the value below 5 hours. On the other hand, because we need to apply the second distributions in the long term, so that means the long-term values are caused by the second mechanism. So this statistic distribution analysis become a tool, allow us to understand what would be the possible mechanism with a different timing range. So if based on this graph, we can understand if we have the failure time below 10 hours, that probably we have one specific degradation mechanism. And if we have a failure time between 10 to 100 hours, because that has another failure mechanism. So in the future, as long as you see the experimental value data cannot fit it by the one single distribution, can be fitted by 2 or 3, that means there are several possible failure mechanisms leading to the different distribution data. So in this graph, we have a 2 failure mechanism. So that's the important implication coming from this distribution data set, because that can give us a hint that we have to be aware of that below the certain criteria, for example, in this case, below 5 hours, we have one mechanism. And beyond the 10 to 100 hours, we have another mechanism. So now we would like to show you an example that how do we use a hand calculation to make the wave plot. Of course, nowadays we have lots of the software, or even we can simply use Excel to make the wave plot. But it's better you have to use your hand calculation at least once, and you will know the details inside. So this is some example, and then some of the typical schematic for the TDB experimental data set. So this is a case where we consider we have we apply the gate bias on the gate dielectric in the MOSFET transistor, and then we start to record our gate lead current versus a time. And then if we stress for a certain time, we can start to see the current will increase. And if we stress for different device that can give us a different the gate lead current versus time, this time dependent behavior. And to make the wave plot, we first have to identify the term where we call the TBD here. The TBD is a term we call the time to breakdown. So this is a case of the time to breakdown data from each recorded current versus time trace during the CVS stress. So CVS is constant voltage stress. Or constant voltage stress. So we give the constant gate bias and recording the gate current versus the time here. And the next question is, how do we define the TBD? So the TBD can be defined when the current exhibits a step larger than a defined value here. For example, if we define our current, if we define our value is here, so that means as long as the current is increased beyond this range, and we define as a value of the TBD, time to break down. Or sometimes we can even make the criteria very small. That has to depend on your device characteristics. Some device you can define value, that the defined criteria that has a very high current, but some case you have to define very small current. So if we define the criteria here, then our TBD is, for example, this, as long as the current increase beyond this defined value, that we consider as a TBD. So this is the first step. So for doing test, we will have this result, the current versus the time. But we need to first to extrapolate the TBD, where time to break down, by using the criteria defined by yourself. So now we have the huge, if we test for the 10 device, so then we can have the TBD for the 10 different TBD, right? So this is an example. So the first device will broken at the 240 seconds. The second device TBD is 191. The third device TBD is 16. So basically we have all these spread data set with the TBD. That's a record come from the previous plot here. So we have this one, but because we will test the 10 device, for sure 10 device won't show exactly the same TBD. So that's our experimental result. But now the next step is that we have to do the ordering the TBD values from the smallest to the largest data set. So this is our raw experimental data. But now we have to do the ordering from this one to the largest this one. So that's the step in the statistics we call the ranking 排序. So we rank. We do the ranking here. So the first stage is we do the ranking, and another one we do the numbering here. That's also the sorting. So we have index the first one where have the TBD 16. Index 2 have the TBD 34. The purpose why we need to put index is because based on the Bernard approximation, the I is index and the N is a total value If you test 10 and then 10 are all fail, so the N will be equal to 10, or the total testing case. So now we can start to hand calculate the CDF. That's why we prefer to use a Bernard approximation, because otherwise it look at the original function of the CDF. This is something, the original function of CDF is something that cannot be precisely calculated by the human being. You need a certain mathematical tool. But with a Bernard approximation, we can easily calculate by ourselves. So this is a case where we have the 10 device value. So we test the 10. We intentionally try to have every device being failed. So thus we have the 10 device value. So in this case, N is equal to 10 here. So now our goal is to calculate the CDF. So this is the CDF. So then the first data, this one, first CDF can be easily calculated. So that is equal to the first one, I is 1. 1 minus 0.3. And then we have test the 10 device. So N is equal to 10 plus 0.4. So then the first value will be equal to 0.067. So this is this one. So therefore, we can calculate all these CDF one by one from here down to the end here. So that's the step, the next one, the second step to calculate the CDF based on the Bernard approximation. And finally, once we have all these CDF data set, we just put in here. So plot the FBI data. So that's FTBD data. That's our CDF in the Weibull plot, where it's showing here. So basically, we just put this one become this. We put in the previous calculate CDF inside this one. Then we can make each CDF has a one corresponding Webbing with respect to the time. So we can start to make this Weibull plot, and then we can start to calculate the slope here, and also the intercept. This is intercept here. So this is the last step here. So of course, if you look just probably like 20 minutes ago or last week, it's for sure the Weibull plot looks very complicated. It's not something we can easily have the hand calculation. But as being the engineers, in the end, we always try to simplify all the case to become the case that we can very easily to get the result. So this is a good example. So in the end, the Weibull plot is very easily to be built, can be built by our hand. So here is one example that you should try to calculate right now to make the Weibull plot, where this is a case you have a 60 laser diode. Because right now, this is a case that we test for 60, but we only have a 7 value. So in this case, the n is equal to 60. So the difference between the previous one is we test each until the value. So n equal to 10 because we only test 10 and 10, all the 10 are failure. But in this case, we test 60, but only 7 value. But not approximation where our ft is equal to this one. I minus 0.3, plus 0.4. This is a total testing number here. So try to calculate right now to estimate the I, the TBD, the CDF. So once you have this information, for sure you can start to make the Weibull plot here. Okay, try to do it now. So this exercise is important because this exercise is related to the homework and also related to a final exam. So it's a good moment everyone should wake up and do some calculation. So you need to at least try once, because if you don't try now, if in the exam, you won't have any time to figure out how to do it. So if you finish, then you can start to have the break. So in this case, for sure, the first we do the index. So we have in the case we have the 7 device value. So the I will be equal to 1, 2, 3, 4, 5, 6, 7. And we do the ranking. So from the smallest one to the largest one. So smallest one is 100, A1, 299, 389, 430, 535, 610, and 805. And we do the calculation of the FT. So the first case, the one with index 1 is 1 minus 0.3 plus, because now we have a total equal to 60. 60 plus 0.4, that's equal to 0.02, 0.012. So that will be our answer. So now, if you have all these FT, so you can make this graph, put here with your time here. So now you can make the Weibull plot. So the answer is in the textbook. Okay, so we'll take a break for 10 minutes. We'll come back at 10:50. 10:55.
最上面请假。OK。I will announce.
Okay.
And I will introduce everyone as a manager.
Excuse me. Yes. I have a question about this. Just like, so it's a slope like usually supposed to be like negative. So the graph is like this.
Yes. It's always in this way. Yeah. It's just always. It should be like yeah.
And then if you like
because of the you can imagine with the longer time the failure rate should be smaller, right? Because this graph is this is time and this is certain negative failure. So with a smaller time, the failure also will be smaller as well. Yeah.
And then if you want to find the y-intercept, that's minus beta and alpha. So how can we find alpha?
Alpha is here. This one. Let me check out. It's so different. This one. So intercept here.
Yeah.
The beta.
Okay.
This is equal to minus beta natural log alpha.
Yeah.
So with a y-intercept, you can get alpha.
Okay, so we get alpha after plotting the chart,
yes.
right? Okay. So then how can we... So if we have this value and we have the slope, then how can we calculate? Okay, I guess like you just use 2 points and start
No.
line.
First, you have lots of points.
Yeah.
You have, for example, you have 10. In this case, for example, you have the 10 lifetime, right? So you can convert 7 to in the x-axis, so you have a 7 point. So each one corresponding to 1 ft. So each one you can also measure 1 axis.
Oh, okay.
Yeah. So you have a 7, and then you can slope is beta, and then the intercept. You have beta, then you can use intercept with the beta to calculate alpha.
Okay. So first you need to draw the chart, and then you can find the y-intercept.
Yes.
Right?
Yeah.
Thank you.
Okay, next we will discuss the system reliability. So far we only deal with reliability and statistical analysis of value of an individual device or component or certain region. But in practical, we actually always use the multi-device. and multi-component structures. So these, we actually use multiple components, multiple devices that can connect it together. So therefore, we have to understand the system reliability as well. So there are two rules when we consider for the system reliability. The first one is a multiplication rule. So the multiplication rule states that the probability of the several independent events will all occur is a product of the individual event probability. So that's we call the multiplication rule. And the second one is a complement rule. So this rule states the probability that an event will not occur is 1 minus of the probability of event occurring. So that means if we have the 90% for the probability of a one event occur, and then by using the complement rule, so that just 1 minus 90% for the case, for the event that will not occur. So I believe you guys already learned all these rules, just probably your first time to hear the English term, but if you try to translate in the Mandarin, I believe you pretty easy to understand all these rules. So let's try to apply this rule in the case of the system reliability. So the system is defined as consists of more than one component. So we have the two system reliability have to consider. The first one is series system. So in the case of a series system, we have an independent component connected in series system. And fails if any of the component, any one of the component fail. So that means if you consider this as a system, if any one fail, for sure this whole system fail. So that's a series system. So the system reliability is a product rule. For example, if each one, your reliability is 97%, so you have a 3 component, so just times 3. The product of the 3 will be equal to the whole reliability, whole system reliability, and then the system value function, which is this one will be 1 minus of our value will be equal to the reliability, and therefore the value is equal to 1 minus RT. And we can also calculate the hazard function, which is a failure rate here, and which is in the end become the summation of the failure rate of the individual component. So the failure rate of a series system is the sum of a failure rate of the individual component. So again, the conclusion is very simple. And reliability of the series systems is always worse than that of the weakest component, because the reliability here is a product of each reliability. So if you have the, unfortunately, if you got the one component only have the 70% reliability, and for sure, this system times together is always worse than the 70% here. So that's the case for the series system. On the other hand, we have another one called the parallel system. So the parallel system, we have the n-independent component connected in parallel. So the system fails when all components fail. So, for example, this is one. We have the 1, 2, 3, 4, all connected in parallel. If the system, the value for system only if the whole R1 and R4, the whole 4 fail, the system fails, right? So if the system will fail if all of the components fails here. So we can have this system failure function and reliability system reliability function. So reliability of the parallel redundant system is always better than of individual component. Sometimes we call the parallel system, sometimes we call it redundant system, because we have some some component as a backup. I think that even you don't hear about the series system or parallel system before, but these concepts already used in our daily life. You will try to parallel several, or for example, you probably will back up your personal information not only in the hard drive for your laptop. You will also back up in the cloud. You also have another portable hard disk to back up all your personal information. So that's the case of the parallel system, or we call the redundant system here. So reliability of the parallel system is always better than the individual one. So here is an example. We have a two component with a constant failure rate around this, and reliability after 1,000 hours is equal to 90.48%. But if now we consider as a double redundant system, so we have a two component in parallel, actually we increase around 9% of our reliability. So this just some mathematical equation to formalize what you already have this concept in your mind, because we all already know that we will put some backup to make sure that the system can be more reliable. So now we have to also understand the physical meaning of the value distribution function in this class. Although in this chapter we mainly talk about the mathematical equation, but in the end we still have to connect with our physics understanding for the semiconductor device, especially related to the reliability mechanism. So again, we have to re-mention the concept of the weakest link. So if we have the value probability, if the F is a value probability of a length L breaking, then 1 minus F is a probability of the survival, right? So F is a value, so for sure 1 minus F means the survival. So similarly, we can also consider original. We have the huge. This is a whole certain of the length with L. But now we can divide the L into the small dl. So then we can have this one as a dl here. So 1 minus F is a probability of the survival for the whole length. Similarly, the survival probability of the infinite small link is 1 minus df, right? So now we consider in this one. So therefore, the survival for this small part is 1 minus df, where df is a probability that length dl breaks. So we might equate the survival probability of length L to that all of its links as become in this way. The 1 minus F will be equal to 1 minus df L over dl. So the reason why we can write like in this is a mathematical trick. The easy way to understand this equation is you just consider if once our dl is equal to L and this is equal to 1, so this function will be back to this one. So that's the most easy way to understand. So we just try to use some mathematical trick to rewrite this equation as has a form like here. So now if we plot the log, then we can come up with this equation as well. So when df is small, then our natural log 1 minus df is equal to df. So therefore, the f is become 1 minus exponential L df over dl. Where this is the value, the probability of the whole length value correlate with the probability of the small length value versus the small length. So that's the equation we can have so far. So now we expect the dF over dL will physically depend on our stress, applied stress, sigma here. So the dependency of F on L can be modeled in the various way, but it is common to assume a power law relationship where our dF over dL is equal to this one, and where our L0 and N are the constant. So therefore, with this consideration, we can again to rewrite F is equal to 1 minus exponential minus L over L0 times sigma 0 and here. So this is considered as a length, but now if we consider the applied stress here is, for example, electric field. So the electric field is an applied stress. For example, the electric field is here. So then we have to generalize this to the case that we are interested in. We are interested in the dielectric breakdown. So, and the stress here is electrical field. And also, the electrode area is A rather than length, relevant length. So in the previous we used the length, but now we consider the dielectric breakdown. So in the case of a dielectric breakdown, as we already draw, that's a typical two-dimensional schematic, but in reality, our device has a three-dimensional directions where our gate dielectric or gate electrode is a big area A here. And then we can divide this big area with a smaller area where that we can consider the smaller one as A0 here. So now with this consideration, we can reconsider the case with the length becomes the area that has a schematic showing here. So the total area is A, and then the small area here is A0 here. So with a similar concept, we can start to rewrite our equation. F is equal to 1 minus exponential minus A over A0 bracket. Now, because our stress is electric field, E over E0 So this equation is powerful because we can start to estimate the value with considering the area factor. So now we have the function allow us to estimate the value respect to this one versus this one. So that can give us additional tool to consider this area scaling here. And this three-dimensional also can be considered have the weak link phenomena, because as long as if you have one place broken, then all the electrons will prefer to only go through this broken place. So that still have the weak link. So when we talk about the TDDB later, we will talk about the area scaling, and we will use this concept again. By using this concept, we can scale our waveable distribution with a different area size. So the next one is the arenas model. So we have been talking about the arenas before, but now we will start to really consider use the arenas to understand our degradation. So this arena equation is not only a mathematical equation, but also can give us some physical understanding. So this is a typical equation for the arenas equation that we have already described before. And the NTTF is one of the targeting parameter, but can be replaced to any one we are interested in. So for example, we are interested in the NTTF. We can also interested in the threshold voltage shift. We can also interested in our resistance. We can also interested in our gate current increase. So basically all kind of the shifting parameters that we are interested in, we can always use the arenas equation to calculate the activation energy here. And here is an example. If you look at this plot, this is a NTTF versus 1 over T. And based on this experimental result, the activation energy is 1.03. And what we use to estimate, how do we estimate the physical meaning of these activation energies? Usually we'll look at the literature to see any reported mechanism has a similar activation energy or not. So now, if we look at this table, we found out that in the case of the surface charge between the silicon dioxide and silicon, this value mechanism can lead to the activation energy between 1 and 1.05. And another one, this one, and dielectric breakdown have the activation energy around 0.2 to 1. Or for example, charge injection has activation energy around 1.3. So once we get this value from our calculation, where we get 1.03 electron volt, and then we look up the literature, find out that someone in the past will also find this value and indicate this value is related to the surface charge. So now we can start to think about whether the surface charge can be the possible mechanism based on this arenas plot. So that's the usual way we use this activation energy. Activation energy is not only the pure number. In the end, we need to use this number go back to check literature, and then from literature we can understand what actually the mechanism responsible for this activation energy. So this is something we have already shown to the arenas part. And sometimes, as I say, in the case of distribution, we might see the two different distribution data that suggests that we have two different mechanisms. But in the arenas part, we can also very often to see with a certain condition, we get a one activation energy. So this is a mean time to failure versus a device temperature. So now we can see the values with this high temperature, there's a one slope. With this relative median temperature has another slope. So this slope indicates the different reliability mechanism. We can also calculate the activation energy based on this plot. So with this arenas plot, we get the activation energy for 2.2 electron volt in the case of this region. On the other hand, this region also gave us another activation energy, which is 0.6 electron volt. So in the end, based on the arenas plot, we can understand there's a certain device. This is a high electron mobility transistor as a function of the device temperature. With a one temperature region, we have a one mechanism. And beyond a certain temperature, we have another mechanism. So this is how this arenas plot can tell us we have two different mechanisms. And I think it's quite makes sense because you cannot expect the semiconductor in the all different temperature always exhibit the same phenomenon. That's for sure. If you beyond a certain temperature, it definitely will start to exciting another mechanism, and that will be also reflect in the case of the arena plus as well. Okay, so with the remaining time, I would like to start to talk about something related to our group presentation. And before we do this, I want to do the roll calling to check your attendance. So, 陈玉安、王正照、左宇腾、陈瑞宇、徐艺熙、黄国文、 洪承伟、廖玉杰、李奇阳、柯宏泰、吴奇洛、廖伯全、李金选、杨志豪、朱义文、刘继煌、彭修颖、陈启安、沈伯君、黄之涵、汪潘爱玲、伊凡、Anna、张怡良、史淑慧、谢立伟、孙礼全、郭安成、杜瑞慈、陈怡轩、崔定和、魏玉婷、魏宇阳、陈新威、车浩恩、吴家明、张浩伟、黄成颖、李进佳、陈鹏猛、林佑廷、郭品轩、高宇和、李炳轩、卢沙特、谭义阳、潘氏经营、陈鹏宇、王松纯、常佩杰、萧元玉、蔡庆辉、邱冠祥、陈定乾、刘桂宏、林冠汉、邓有福、周燕婷、戴文祥、Okay, so I will spend just a few minutes to explain how we are going to arrange for these group presentations and something that you should know about this. So, as you know, we have the 4 topics. So, finally, we finish all related to the mathematics part. So, in the following courses, in the rest of the semester, we will mainly focus on this. And this 4 topics, we will focus more on the reliability physics. We will tell you how this reliability, how do we test, and how this reliability should come out, and what would be the general understanding, the reliability mechanism, the physics-based mechanism related to this 4 parts, and what would be some of the issues remaining. So the first one is the bias, the temperature, instability, and interface traps. And the second one is time-dependent dielectric breakdown. And the third one is a mass transport induced failure. And last one is we also will cover the electrostatic discharge, ESD. So each topic, because we have quite a lot of students here, so actually the presentation is not that long. It just give everyone the chance to practice your presentation, to have a chance to work with your teammate, and also give you the chance to practice your English. So I think nowadays that definitely the English is one of the most important, like the tool you need to at least basically to speak. This is a presentation, not like the like the random speech, just call everyone to speak 5 minutes about yourself. This is a presentation you can prepare at home, so that should be quite not that difficult for everyone to practice in English. So the most important is we have some of group have 5 people, some group have 4 people, because we have a total 59 students here. So each topic will only take around 20 or 60 minutes, depends on your group size. But the most important is this one. The student from the one group, student for the presenter is randomly select. That's because of, for example, if you have 5 students in your group, and then the order of your presentation is randomly selected by me, not decided by you. And also, the duration for each presenter is determined by me as well. So probably someone has to speak only 3 minutes, and somebody has to speak 5 minutes. It depends on my feeling. And the goal is try to avoid that there's only the one person who take care every part. So this is sometimes we say the worst teammate, the 猪队友. So that's it's usually happen in a group war that always there's a one hero guy who is work so hard to take care everything, and there's always some not good, the poor teammate who doesn't care about this presentation. In the end, the people who work hard has to take care every preparation and also try to cover lots of the presentation. I think it's not good. As I said, the purpose is try to give the chance that everyone should be a nice team to work with everyone. So with this rule, so you won't know which part you should present it, because it's all determined by me. So only thing you can prepare is you need to understand everything. Otherwise, you will be certain have a problem during the presentation, because it's randomly determined by me. So you're likely to be picked up in the parts that you are not familiar with or you are not prepared. So what you have to do is you have to work closely with your teammate and make sure that you can understand all the parts. So that's, and then from the presentation, you're familiar with the presentation, I can simply understand the scope that I should give to you, because if you don't well prepare, I believe you cannot present the things very well, and of course your score will be lower. So the score is determined by person. So the score I give is person by person. It's not like generally whole group will get the same scores. So the idea is, of course, I will still give a general overview for each topic. So each topic I will give you probably 2 hours, 3 hours, depends on the content of the slide. So, but you only prepare for 20 minutes, so that's not difficult, because you have all slides already. The thing I want you just to make sure that you can use your own language to express your ideas. And also I will upload some more reference in the new E3, and also some of the slides from the last year or several years. I will upload some example slides from previous students for your reference. And you can use my lecture as a basic foundation. So because my lecture is covered for 2 hours, but you only need to prepare for 20 minutes. So basically you can take my slide as a basic foundation, but then make your own way to tell the story. And please work with your teammate. So my suggestion is, for sure you still need to divide the work, but then you need to make sure that each member has to understand his or her part and make the slide for his or her part. And each member has to teach other people about the part that he or she is responsible. So I think that would be more efficient. In the end, I think everyone can more easily to understand, because you probably, for example, let's say, I think most students will be divided by the slide number. If it's a 20 minutes presentation, probably you need to prepare 20 slides. And for sure you can divide, you have 5 people, so each person will prepare 4 to 5 slides, and then once you prepare, you have to present to your member, you have to teach your all the members, because likely your members will present your part during the real presentation time, and you also will be asked to present other part, because I don't know who prepared which part. I just randomly select. And here is the evaluation. So the contents, for sure, the content is made by a group. So I still give the content for the 1 score for each group. But there's another part for delivery. So delivery is determined by each presenter. But also, I want to put a very strict time control, because a good presentation should always consider the presentation time should not be too limited or too lengthy. Should be well controlled with the talking time for the 20 minutes. So there's a time control will be taken into account for the scoring as well. Then this is how I calculate with the time. So idea is, for example, if you get a 90, you get a 90. And then, but unfortunately, your group presentation time is 22 minutes. So what I do is, I will do the reduction based on these additional 2 minutes. So that would be the score. So basically you have a 90, but now you have the 2 minutes exceeding the targeting time. Or if you only presented for 18 minutes as well. So basically if you have a 2 minute exceed time, that will reflect to your total score as well. So what you have to do is you have to practice with your teammate and make sure that you can, your presentation time should be as closer to 20 minutes as possible as you can. Otherwise, you will always have the score will be reduced. Even you have 90 minutes or 90 minutes 30 seconds, but the best way is you have to practice to make sure that your total presentation time is very close to 20 minutes, and then you won't get the score reduction here. And also you need to send me the slide 1 day before your presentation. So that's the 9 p.m. You need to send me the slide 9 p.m. before the presentation time. And let's look at the schedule for the rest of the class. So time flies. So we are in the middle of our semester. So now is the rest of the semester. Today is 10/14, so we are the 7th week. So this is the schedule from the next week till the end of the semester here. So we have the next week, we will talk about the BPI interface trap. And then also next week, we'll talk about the TTDB. But also, I will provide you time that you can discuss your teammate at your class. So probably today, in this week, we will only talk about probably like the half class. And you will have another half class to discuss with your teammate for the presentation. Of course, you still need the time to discuss the presentation offline, not only in the class, because if only in the class, you're still not enough. But I still try to arrange sometime because I know everyone is very busy. So then the first group will be requested to present at the November 20, and second group is here, November 18, and this is December 2nd, and also the December 9th for the last retention. And the final exam right now is tentatively decided in the December 16, but we will still discuss later on. So that's still to be determined. If there's any delay for our schedule, for sure that we will find another time for the final exam. So now it's time that you have to, I already assigned the group, so it's time that you have to meet your team members. So I will call your name, please raise your hand. So 卓宇涵、史淑慧、魏玉婷、卢沙克、洪成伟. So that's your group. So it's better after we will end up today. We won't move on. So after I call the name for each group, it's better you have to meet up your teammate and to have a certain connection. And second, 林志汉, no, sorry, 邓有福, 徐艺兴, 朱义文, 张怡良, 蔡庆辉. The third one, 王正照, 陈其安, 张浩伟, OK, 郭品轩, 常佩杰. Next one. 伊凡、孙乃全、陈怡轩、陈鹏某、谭义阳。Next one. 李奇阳、杨志豪、安阳、黄成颖、潘世金颖。Okay, the next one. 陈立谦、刘冠宏、陈鹏某、李进佳、陈新威。Next one. 周燕婷、戴文祥、邱冠祥、崔定和、杜瑞慈。Next one. 陈玉安、吴奇洛、廖伯全、刘继煌、黄之涵。Next one. 谢立伟、郭安成、魏宇昂、林佑廷、肖元玉。Next. 陈瑞宇、黄国文、柯宏泰、李金璇、车浩恩。Next one. 彭修颖、胡家明、高宇和、李炳轩、林冠汉。And last one. 廖玉洁、沈伯君、汪潘爱玲、王松纯。Okay, so we'll stop here. So it's time you can make to connect with your friends. And I know some of you might not be here today, but I will also do the polling again next week. But I guess at least more than 90% people are still in this classroom now. If any question, just let me know.有人不知道自己的 group 吗？如果有人不清楚自己 group， 可以再跟我讲。If somebody don't know which group you are belong to, just let me know. I will call the name again.
I mean, VTI 1, I think.
Your the one is 史书柜，哎，这我，左手。
现在